Hi everybody. I thought I would show you a cool electronics project I just finished up. This is a little home-built oscillator, and it's based around that chip in the middle of it, which is called a 555 timer chip. And I'll go over the overall layout of it here. First, let's turn it up, hear what it can do. Neat, eh? So here's what it does. This knob right here, this controls the frequency of it. This one controls the pulse width, and this is just a volume knob right here. Just because of the simplicity of the design, the pulse width is also somewhat tied to the pitch of the unit. So whenever you adjust this, it also will adjust the pitch. Mostly notice it at higher frequencies. Cool. Well, let's go over what else is going on here. There's a capacitor right here, and that's a 10 microfarad capacitor, and that gives it the overall frequency range that it has available. I think in the future I would use 2 or 3 different caps and then make them selectable through a switch, so that you could choose a lower, a medium, or a high frequency range with it. I have an LED indicator here, and it's not tied to the volume of the unit. It's just tied to the width of the pulses, which is pretty cool. Let's turn it up here. So as the pulses get slower, the LED goes along with them. Cool, eh? At a certain point, you can't really notice. Right about there. It just stays on all the time. Okay, what else is going on here? That's the actual timer chip right here. There is a resistor. It's tied to the output potentiometer here. And that just limits the amount of volume that comes out of the circuit to go through the speaker, so that it isn't too loud and doesn't. Basically, it's just so it's not too loud. And this is a cap that I'm not going to bother explaining what that does. And here is a resistor. This is tied. Basically, the output pin on this chip, which is number 3. Which is 1, 2, 3 right there. It goes to the output potentiometer here, but it's also going through this resistor in a parallel circuit, and that resistor goes to the LED. If I sent the output from this directly to the LED, I think it would risk burning out the LED. So I put a little resistor there to put it at a nice bright level, but not so bright that it would actually damage it. Anyhow, let's turn it back up here, and then we'll check out the oscilloscope so you can see some of the waveforms. Just looking at the rest of it here, I've got my oscilloscope kind of wired to it right there. Big shout out to Chris Vesey for hooking me up with this sweet oscilloscope, and just a regular 1/4" output. So let's go here. Oh yeah, I think it's also worth noting that the this resistor, I also chose a value so that it could drive a speaker directly from the chip. I'm using a 6-volt power supply right now, but it also would put it into the voltage range so that I could record with this as well too. I believe that the output voltage is somewhere around 1 volt or so, so that I should be able to actually record through with this, or and not ruin my audio interface. So without further ado, let's turn it up again here, and let's check out the oscilloscope. There we go. So it's got a pretty even pulse width right now. The frequency also is somewhat tied to the pulse width. Once again, just because of the simple design of it. There's only a few components here. So if I turn up the pulse width knob, you can see the bottom of it getting much narrower. There it's wide. Much narrower. And you can hear it too. So let's keep that up some. I'm going to turn our frequency way up. It starts to actually round off the waveforms, and I believe that's because the circuit is just or components are having a hard time keeping up, so then it starts to round off the edges of them. Right about there. Alright, I also thought it might be kind of fun to see what the frequency range is on this, and also to see what the output voltage is, just to confirm my suspicions that I had from earlier. And so I've wired up my voltmeter here to it, and it's got the output jacks there, wired to the ground right here, and then also wired to the positive, which is the tip of the connector. The volume's turned down right now, so we can't really hear anything, but I'll turn that up. And then we're going to keep an eye on the notes here. This is an auto-ranging multimeter, so right now it's reading somewhere in the range of 3 millivolts. I believe that somewhere in the range of 1 volt is line level. So here we are, full volume on it, and it's reading 0.7 volts approximately. Let's see if that changes as I change the frequency range here. Yeah, it goes up. Wow, how about that? I'm reading 1.1 volts now. Well, how about that? As I keep the pulse width up, but turn the frequency down, that really gives it a much higher voltage, 1.47 volts. Let's see if I turn this pulse width down if it brings the voltage down again. Yeah, look at that, it does. Cool. Let's see, can't seem to make up its mind. Cool, okay, so let's put this into frequency mode, and let's see if we can see what frequency it is. So I'll take my meter and I'll flick that over here to the hertz setting, and that might already be reading it. It's saying about 11 hertz right now. Let's turn up the volume. So 22 hertz. Okay, so at its lowest, it'll put out a frequency of, well, basically 10 or 11 oscillations per second. So let's see how high it will go now. So I believe to get the highest frequency, I have to turn this pulse width all the way up. Okay, we're already at 37, and then if I turn the frequency, I might note that the frequency is wired in reverse. So about my earlier suspicions confirmed by adjusting the pulse width. It also changes the frequency. Notice how low the frequency is now in the 40 to 50 range. So I turn up the pulse width, raises the frequency, and I get a maximum frequency of about 1 kilohertz. 1,000 oscillations per second. So down to about 10 or 11 oscillations per second. To about 1,000. Neat. Alright, cool. Thanks for checking out my video. Have a nice one, everybody.